Yeah, I'm Daniel Parker. We work with Structural Integrity Associates. I believe my colleague Andy Coughlin as well is on this to possibly answer questions. Our company primarily it works in the power industry generation sector, nuclear, fossil, hydro services. So this project or this presentation is going to be kind of directed towards that type of infrastructure and assessment of the what we're considering that as the critical structures. As everybody's heard, I'm sure over the years, it always comes up that the infrastructure within the United States and pretty much worldwide is old, aging, in risk of failure, and the costs of repair and mitigation issues are quite high to take care of aging issues that range from chemical attacks, ASR, just poor design, and various other environmental and extreme loading events that are possible, sometimes not accounted for in the original design process. It's kind of the obligatory ASCE grading chart that again kind of shows that overall our infrastructure is in poor condition. So often structures are kept in service beyond their original design life. Many are held during relicensing and various items. Many structures are kept to original design basis code requirements consistent with the time the structure was designed. This is common in the nuclear industry, where something might have been built based on AISC 6th edition, and you go back and relicense and look at things at that versions. But sometimes eventually evaluating the older structures using current code requirements can potentially affect original safety margins, both positively and detrimentally. Increased capacity limits can be established for steel welded and bolted connections and utilizing actual concrete compressive strengths above original design strength. Actually, the earlier presentation by John kind of touched on that with the significant amount of testing that they saw, where they were able to actually get some increased concrete strengths as well as some of the geotechnical foundation bearings. So that kind of identifies where that can come in, but also things that can be identified is particularly in concrete structures, older design methods can actually reduce safety margins, as well as additional factors that can affect service life are going to be environmental conditions, consistency of materials, quality of construction, and loading conditions. Basically, all infrastructure, new and existing, is susceptible to degradation that comes with aging. Accumulation of damage and structures subsequent failing is sometimes difficult to predict due to numerous real-world factors. Some of these factors can lead to some structures failing prematurely and others lasting well beyond their original design life. And these listed here are just various things: chemical attack, overloading, increased design loads, changes in design code requirements, etc. Again, many of these high consequence structures, bridges, dams, power generating facilities, they're in life. A lot of them have exceeded their either licensed or design life, but replacement is definitely prohibitive due to cost, the value of, particularly for power generation utilities. There's still revenue producing assets, and a lot of times in cases of dams and things, failure would have definitely significant consequences beyond lost revenue, but loss of life. So it's important to identify structural vulnerabilities and designing retrofit modifications to economically extend the service life of these structures. Currently, there's like no single agency that oversees these various types of structures. That could probably be looked at both good and bad, depending on how you want to look at it. But generally, these different highway structures, railways, dams, locks, the associated different regulatory bodies are I've listed there, but generally, even though they're not all one umbrella, they do have kind of a common mission to keep asset owners accountable to maintain their projects. So as the structures reach the end of their design service life or asset owners are looking to extend their service, regulators they're require the owners to demonstrate that the structures can still maintain their functionality while posing low risk to public safety, regardless of the expense of the owner. So that's definitely the good thing about the regulations. But then it's important that asset owners, if they could develop a health monitoring system, which is robust inspections and various things. It's definitely beneficial if they can continue to keep their assets safe and functional. Not only are they generally profit positive, the costs of decommissioning, removal, remediation of project sites can be get very large, that are not in the owner's financial interest, and as well as Julie was just talking about, just in general, the waste and just losing that locked in carbon and everything to keep it within the structure, and being a positive asset is important. One of the important things, a part of like the health monitoring system is like the monitoring is either intrusive or non-destructive examination techniques. That'd be instrumentation, monitoring, occasional core sampling of concrete to evaluate strengths and everything. This is important to where if you're doing the monitoring, it will allow the owner to understand if there's like changes to strength or capacity of their structures due to accumulated damage. Again, this damage could be either from unexpected or beyond design basis loadings, earthquakes coming in larger than they were expected to be, possible blast, terrorist blasts, various things, environmental damage, long time environmental damage, or chemical attacks such as AAR or ASR. And it's beneficial for the owner to keep a measure of that. So moving forward, so for what can be done to help assist the owner is that what we're calling this fourth dimension life cycle assessment is setting up analyses and assessing structures essentially from cradle to grave, so that we can kind of create a model that will change with time, with aging and degradation. What's important to that is to be able to evaluate the structures during beginning with construction. This lends itself more towards larger mass concrete structures, which are more common in the power industry sectors, dams, lock walls, and just larger like nuclear reactor or containment buildings, various things, very thick walls. So what important for doing evaluations like this is what we call nonlinear incremental structural analysis. It's basically a combined thermal, mechanical loading analysis where basically the stage construction, including heat of hydration to evaluate thermal stresses, coupled with nonlinear time-dependent aging, creep, shrinkage as the concrete goes from initial set to maturation to help identify potential, essentially primarily for cracking. And this would be best be performed before construction so that any potential issues due to placement sequencing, either time or duration between lifts, or how long you might need to leave insulation covers on to reduce thermal gradients, various things like that can be identified, and mitigation strategies before construction can be implemented. This isn't always the case, but it's helpful if in particularly large mass pour concrete structures that this could be evaluated. After we do some type of an analysis like this, we would have essentially a digital twin of the structure for use in subsequent evaluation. That means I see a lot of times where somebody wants to look at an analysis of say an intake tower for a reservoir for outlet works or various other structures, and they'll come in and they'll look at the plan sets and create their finite element model and build it based on what the design specs are. And it's like, well, that's well and good. You have a nice model, but is that really what you have out in the field? So it's important to not only try to get a good idea of where you're at based on the construction sequencing, but to also incorporate in-service degradation that is either picked up on during monitoring programs, either obviously inspection, regular inspections to look for just damage, which again would be looking for possible ASR issues, chemical attack issues, as well as records of any type of large beyond design basis loading, changes in basically geotechnical issues where which we see a lot here in California, is that the seismic hazards, site-specific seismic hazards seem to go up at least every 5 years. So in particular, looking at some concrete intake towers and dams for hydro facilities. They're looking at ground-based spectral acceleration records of 1G, which is not what a lot of these structures were designed for, particularly when you got a lot of older structures that are built in the 1950s and even earlier. So incorporating this type known degradation, supplementing it with testing data to evaluate the dynamic characteristics can be incorporated into your finite element models, and using sophisticated concrete constitutive models, we can get the better predictive models to evaluate the performance of a lot of these structures to help extend the service life or provide support for extending license periods. So this is a plot we kind of came up with to call it our time-dependent margin plot. So basically, during new design, over on the left side of the plot, where you have new design, you have like an initial safety margin. As you progress over time, there could be damage to the structure, whether it's well, it can happen anywhere, because again, like the probability of like return periods on earthquakes or probable maximum floods levels, they can happen equally on day 1 or as on day 50. And there could be, again, multiple earthquakes or other large loading base or loads that will generate cumulative damage, compounding with various other environmental factors. It's going to, over time, you're going to have degradation and changing the capacity of the structure. Where on the other side of the equation, demands, again, can potentially increase prior to the end of expected service life. Many of these are, like, again, increased site-specific seismicity, greater temperature fluctuations with climate change, changes in hydrology levels, whether a lot wetter in some areas, a lot wetter, a lot more higher probable maximum floods. And so that safety margin or the performance gap is it will increase over time. So it's important to try to incorporate all these known issues or identify these issues into modeling as you move forward, instead of just trying to take like the design basis spec drawings of various and come in and think you're going to do some seismic analysis or modeling. You need to include degradation within the structure. So this leads to, tough questions. How can, listed here, I use earthquake because, again, I'm California. Most of my work is looking at seismic demands, but if other loading conditions, pick your poison. If it's high wind loads or various other issues in other parts of the country, you can fill in the blank. But it's important to evaluate all the aging characteristics, changing in loading, and how much, determining when structures are going to be safe, unsafe, and how can that be done. And we believe these can be answered with time-dependent life cycle modeling. Will help asset owners rank what their highest risk assets are so they can prioritize rehabilitation and remediation, because obviously there's either limited funding or how much asset owners actually want to try to sink into their assets. But obviously for most energy in the energy sector, they're profit positive revenue sources that they would really like to keep in service. And so we believe doing this fourth dimension of including aging and degradation into a more typical or make them not your typical finite element structural analysis, seismic performance structures, but to incorporate this aging and degradation to get more realistic models and analyses are beneficial to keep our infrastructure up and in good health. And that is all I got. Thank you.
Thank you, Daniel. That was very informative. Are there any questions that we might have for our third speaker? Daniel, we did have one question. What types of knowledge, policies, and other standards are needed to facilitate adaptation and reuse of existing concrete structures?
I'm sorry, can you repeat that?
Sure. What types of knowledge, policies, and/or standards are needed to facilitate adaptation and reuse of existing concrete structures?
Well, let's see. I'm take it from, from a lot of the in the power industry. A lot of it is not so much adapting or reusing. It's trying to keep everything working as it was originally designed for, which is for either housing a nuclear containment facility so it can either have extended life, making sure dams are safe, and take tower structures for outlet works or continued. Basically, they're operational and functional for what they are. There's in the power industry, there's not really, I think, a whole lot of I'd say reuse, as in Julie had some very nice examples of older buildings, either older office buildings or various industrial buildings that converted to apartments and various things like that. I'm not sure that I'm seeing uses like that for power industry structures.
Thank you very much.
Yeah. I could add to that. I'm sorry. This is Andy. I feel like the contributions of ACI over the years for how we can model concrete shrinkage and creep in a time-dependent manner, as well as heat of hydration in a time-dependent manner, have been able to be employed in projects. And unfortunately, we didn't get the approval to share our case study because of confidentiality reasons. But we like that consensus industry standards, and we think that ACI could make more on longer term degradation modeling standards for modeling the long-term degradation of concrete.
Thank you. Julie, you had something to add?
Yes, actually, it kind of goes back to what was presented earlier about maintenance programs. I think really what's important when understanding concrete, there's a variety of things that you really must understand. One, service life modeling is extremely important, and understanding what the loads are going to be on that structure, and not the loads, the historical loads, but also looking at the loads of the future, because they are changing with the change in climate. Case in point, we're seeing higher temperatures, as was discussed. We're seeing higher water rise. If you look at Venice, it's underwater half of the time. So there's many things like that. And then you need to combine that with the life cycle costing and also the life cycle assessment. When we go on to maintenance programs, which I really see lacking here, is if we compare this to what's done in Japan, Japan actually has a very, very high governmental inspection program of their infrastructure, where they have people going out on a monthly basis to see what is going on with the infrastructure, not only because of its use on a daily basis, which I kind of look at as your basically your day-to-day stresses, but also after any acute shocks, which include your earthquakes, include floods, hurricanes, tsunamis, so forth, and etc. And they've gone out and they've trained people to go out and be inspectors. And if anything, I see that as why we're starting to see that become involved in ACI. I would like to see more of that in structural inspection, of a certification that could be gained, so that people could understand what they need to be looking for, why these occurrences happen, and then the remediation that can happen to help the structure extend its service life.